All right, recording where you roll in. Let's look at new posters. Actually, these are posters that you guys do already have access to. Look at wait, okay, wait, I got this right here. Okay. So you guys remember the last couple of weeks we've been doing energy, and all the green banners are energy related posters, energy work. If you flip it over on the back side are a bunch of blue banner posters. These are all related to the stuff we're starting today. Right, so you got momentum, impulse is what we're starting today. So you guys should have access to all these posters I'm about to go through. And so what is momentum? So the symbol for that is lowercase p, and it's very simply just mass times velocity. That's it. Momentum is mass times velocity. Okay. Ooh, what is, you guys might remember this. What does that little arrow above the variable mean? Vector, yeah, vector quantity. Okay, so we're back to vector values, right? You guys haven't seen vectors in a while. Last couple of weeks when we've been dealing with energy is like scalar. It doesn't really have an associated direction, right? But momentum does, and it's going to be an important aspect of it, right? So momentum, mass times velocity. Okay, so velocity is also a vector. Actually, I could have put those vector arrows above forces, above accelerations. Could have done it too. Right? See, mass is a scalar, so that's why it doesn't get in there. So momentum is something that's conserved within closed systems. I should say within closed systems of the universe in general. Right? If you add up all the mass times velocity, that's okay. And what is this useful for? What is this framework good for? It's good for anytime you see a collision, right? Unless something is colliding with a spring, but for general collisions, if you have like masses against masses, two asteroids colliding in space, or like a bat hitting the ball, or okay, you want to think in terms of this framework that we're starting today. Right? So momentum and collisions go hand in hand. So let's look at just some general collision. We have two masses. They've each got their own individual starting velocity. Oh, so mass A, velocity A initial, velocity mass B, velocity B initial, and then bam, and they collide. And then what happens? Well, there's like a bajillion different things that could happen depending on what type of collision it is, right? So I just have some generic collision setup, right? Maybe they kind of bounce off each other, bubbling, something like that, right? So, okay, I see collision. I immediately think conservation of momentum. Okay, I know momentum has something to do with mass times velocity. I can say sum of momentum before collision equals sum of momentum after collision. So what does that look like? Oh, it looks like mass times velocity for object A, mass times velocity for object B. This is initial, equals MAVAF plus MVVBF. That's it, right? Momentum's conserved, right? Notice this is all in one dimension. I'm not getting crazy into two dimensions. I forgot to post for that too, but this is all like along the x-axis. Usually AP asks questions like that too, like just along the x-axis. Right? What's about this? Oh, yeah. Speaking of what type of collision that could be, see, like near the end of class today, we'll probably solve at least one of these, just general collision, right? Depending on the types of objects you have thrown against each other, this could play out like again like a billion different ways. Like, what if you have two balls of clay? Like, think they're going to stick together? Right? Versus, what if you have two like super bouncy balls, or how about these like metallic like Newton's cradle balls? It's like really bouncy, right? Ooh. Or what if you had like two half deflated tennis balls that kind of or they kind of bounce off each other but not very well, right? Or like anything in between, right? This could play out like a billion different ways. So, that has to do with like these post collision velocities, doesn't it? Like these post collision velocities, right? And if you don't know what kind of collision it is, or if you're not given both of them, then that would be not a solvable problem. Right? You have to know either what type of collision is specific, or you have to be given some post-collision velocity. Right? Now, if you know, like after the collision, like mass A is going to rebound at blah, 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 if that's given, then in that place, velocity V final also becomes locked in place. Right? And remind you guys too that these are vector values. So the fact that they're vector values, if they're traveling in opposite directions, do you think that somebody has to be positive and somebody has to be negative? Right? And it'd be important to also throw in the negative signs too, right? Last 2 weeks, the negative signs wasn't really a huge deal, right? Get negative speeds, square it for kinetic energy, and it didn't matter, right? But now it matters. It's back to being important again, right? Vector values, direction matters. Right, so let's talk about what kind of collision, right? So we could have like two balls of clay that stick together, or could have Newton's cradle balls that are boing, like super bouncy, or anything in between. Let's look at like boundary conditions, like extreme types of collisions that you could have. Let's start with two balls of clay that stick together. That would be perfectly something, right? And the physics term for that is called perfectly inelastic. So anytime two things collide and stick together, right? All right, well, what's that going to look like? Okay, so I see a collision. I can think of this framework, conservation of momentum. it's going to start out the same way. Actually, that first line is the same one, right? MAVA not and BVB not, just add those here, right? Oh, but look at this. It's just a small modification, like post-collision, right? Doesn't it make one giant mass? Well, moving at some common final velocity. That's it, right? Otherwise, this and this look like nearly the same, right? Okay, so it's just a small modification, so that's not too bad, right? Right, pretty fine stick, right? Versus, I wonder what the other extreme would look like. What if it bounces off each other as perfectly, so it could possibly bounce off each other, right? Which is like Newton's cradle, right? Which is, I shouldn't put this up here with inelastic because that would be the opposite case, right? Inelastic is collide and stick, right? Okay. So the exact opposite case is called perfectly elastic, right? So now here's probably as close as I can get, right? Perfectly elastic is like perfectly bouncy. Is this perfectly bouncy? Okay, there's a little friction loss, but it's probably as close as I can get, right? So when you think perfectly elastic, think Newton's cradle, think the world's bounciest bouncy ball, or something like that, right? Now, what's the physics behind that? What's the physics that marks perfectly elastic? Well, it's two conditions you're looking for. So I got conservation of momentum, although maybe that's not super helpful because this is true for all collisions, right? Some momentum, okay, so momentum's conserved, right? But what makes a perfectly elastic collision perfectly elastic is actually, here's the special condition right here. Say sum of kinetic energy pre-collision equals sum of kinetic energy post-collision. That's interesting. So now we got this new equation, 1/2 mv squared, and I do that for the bits before and after the collision. That has to equate also. Because supposedly that's only true for like perfectly elastic. Now here I've got a system of equations, right? You guys will solve quite a few system of equations in this class. I can show you guys what the solution to that system of equations is going to be. It's this yellow box right here. So this says the speed, or I should say the velocity, right? These are vectors, right? Velocity of object A post-collision, that's what F is final, right? Post-collision equals, and it's this crazy looking fraction right here. This yellow box is the solution to this green system of equations right here. Okay. I should tell you guys too, probably a lot of you guys are going to end up taking physics in college. Maybe if you have some science major, right? One part of physics is going to be collisions. You'll see all this stuff again, right? This yellow box equation right here is not in a lot of physics textbooks, and it's also really hard to find on the internet. And in my personal experience, if college teachers ever asked you to solve elastic collision problems, they have you always solve the system from scratch, right? Which takes a lot of paper and a lot of time, right? So if you're holding on to your notes from high school, from Griffin's class, oh, whip this out. You got the answer right in front of you. Probably save a lot of paper and a lot of time. Okay. Okay. What's I say about this? So let's backtrack a little bit and do some comparisons. So we've got momentum mass times velocity, vector values, conserved collision physics. Okay, so we got that. Right? We've got some general collision. So this could be true for any type of collision. This could field. Right? See things that collide and stick, things that are like super bouncy. Right? Which one of these looks like an easier question to field from AP? Perfectly inelastic or perfectly elastic? Which one looks like easier math, do you think, by far? Yeah, inelastic is by far easier to work, right? And so having read many AP questions over the years, if there's any collision question, like 95% of the time, it's inelastic. Something to do with like colliding and sticking, right? Every rare once in a while, they'll ask elastic, but if they do, it's never something where you have to dig down into like this kind of, they never make you solve the system of equations. You don't have to memorize this and they don't give it to you. I've never seen one. If AP ever asks an elastic collision question, which is really rare that they would, some context I've seen, one is that like multiple choice, you can go through the answers like one by one and like plug in the multiple choice answers until you get something that does satisfy each one of these, right? Although remember, all the multiple choice questions, you should ideally be able to solve within 2 minutes because that's how it paces out for the entire set, right? So like solving it from scratch would take more than 2 minutes. So you have to like play out the multiple choice answers. Or the other way I've seen them ask the question is just very simply, they boil it down to something very simple, like this ball swings on a pendulum, so you have the height change, the speed's gonna be square root 2gh, something like that, right? And then it slams into something that is equal mass, because that helps simplify it a little bit too. You can have this exact model in your mind, think about Newton's cradle, right? Equal mass that started at rest. And say, okay, well, if it was equal mass started at rest and it was perfectly elastic, then I know what that would look like, because I can see right there, right? You got one object slams into the other and it transfers all its momentum to the other object. So you have to kind of memorize that or just know that that would work out that way, right? So, but AP generally doesn't ask you to solve this whole crazy thing. Right.
Let's see what else I want to mention about this. Oh, yeah. Let me go back a little because I do want to talk about contrast these two types, right? Let's go back to this one a bit. So I said something about like for elastic, the kinetic energy is conserved, right? And that's what makes this type of collision special, right? Is kinetic energy is conserved, right? But hang on a minute, didn't we make like a whole deal like last couple weeks about energy in general being conserved? So if it's only conserved for this special type of collision, this elastic, where it's like super bouncy, then what about like anything else? Like what about inelastic, or what about just like in general, right? Some collision that's not necessarily elastic, right? What do you think happens to kinetic energy if you account for that? Let's think it. So I'll give you guys 3 multiple choice options and see show of hands. What you guys think the answer is, right? So suppose you do 1/2 mv squared plus 1/2 mv squared. You say, oh, here's so many joules of kinetic energy to start with, right? And then let's say inelastic collides and sticks. So you do 1/2 mv squared for the entire thing post collision. And you compare the kinetic energy before and after. Is it the same kinetic energy, more or less after compared to before? Right? How many guys think it's this for this type of collision? It would be the same amount of kinetic energy. So nobody says that. It couldn't be because that would put it into this category, which would be like the opposite thing. Okay, so how many guys think that kinetic energy would be shown to decrease from here to here? Shown to decrease. Yeah. There's lots of hands, right? So near the end of class, we might have time for that. Solve one of these, and then I'll do a kinetic energy check. And if you do get the so for inelastic, the kinetic energy will always go down after they stick together. And in general, if you want to make sure you get the time order right, because you can't set up conservation of momentum. It's like, oh, well, let me compare like before and after. It's like, wait, which actually did happen before, right? If you get the time order correct, then post collision, there will be shown to be a decrease in kinetic energy. You might say, well, hold on, I thought energy was conserved. So where does that energy go? Does it like disappear from the universe? And the usual textbook explanation is that it goes into like permanent deformation is usually the bit, the biggest place the energy goes. So if you have like 2 balls of clay that stick together, ooh, do you guys think there's a lot of force times distance that goes into like deforming those balls of clay? Okay, that's probably where the vast majority of that mechanical energy went. Is like permanent deformation. If you have to write out an FRQ paragraph, you might want to mention that phrase, like, oh, permanent deformation. Right? And oh, yeah, this student knows what they're talking about. You might also say like maybe thermal energy, maybe heats up a little bit, maybe sound energy. Here, ooh, I can hear it. Finally, last thing about this one is, what if you filmed this with a camera and then you played it in reverse? So instead of 2 objects sticking together and move on, right? What if you ran that in rewind? Pow! Ooh, would that look like an explosion? An explosion? I think that would, right? One of the questions I'll throw at you guys is, oh, what if you like throw a grenade across the room, right? And then it explodes midair, right? And it would be this, except backwards. So you have one giant grenade, you have some initial velocity, just watch the subscript there, the initial, and then it, bam, explodes into 2 individual parts, each with its own individual velocity, right? Right? Now, momentum would still be conserved, and you can use that to figure out like the center of mass of the object would not change what it's doing, as a giant object. What about kinetic energy? So suppose you throw it and it has like 100 joules of kinetic energy flying across the room, and then bam, it explodes into 2 different parts. Do you guys think? What do you guys think happens to the kinetic energy from that point of view? Does it increase? It is an exploding grenade, right? Yeah. I think the kinetic energy would go up in that case, which is actually consistent with this, right? Because 4 at a time stick together, K kinetic energy goes down, the explosion, okay, would increase. Now that kinetic energy comes from somewhere. Oh, I bet it comes from the chemical explosion inside the grenade, right? There's some kind of chemical explosion. Okay, that's where the energy is coming from, right? This doesn't appear from nowhere. All right, so we got that. All right. Later this week, I'll set you guys up with a couple of labs, like collision labs. I've got these collision carts. Now, I don't have the track in front of me right now, but these wheels like lock into grooves on like a flat track really nicely. It's like a low friction type system. These got little magnets in them, so they'll like bounce off each other really nicely. Right? It could model probably something pretty close to an elastic type collision. You can put lab weights on here, change, say what happens if we got these different. Okay, so you keep track of different masses, maybe at different pre-collision velocities, then have different post-collision velocities. And ideally, the momentum should be pretty well conserved, like before and after. Right? We can also modify this to make an inelastic type collision. I bet what I could do is I could take one of these bar magnets and stick it to the front, this one, and then take another bar magnet, stick it to another one, right? So the got north and south, so they stick together. And then you could do a really similar type lab that would just be for the special case of they stick together. So that'd be an elastic type collision. Do that. So you guys get your hands on those later this week. I got planned. All right. So we got different types of collisions going on. Remember, here's a general collision, conservation, momentum field, all those. Okay. Perfectly inelastic is one extreme. They stick. Perfectly elastic is the other extreme. They bounce as well as they could ever possibly bounce. Okay. But how could you quantify how bouncy is something? Like, what if you have two half-deflated tennis balls that kind of bounce off each other? Okay. Oh, here's a way you can quantify how bouncy is something. The physics term is called coefficient of restitution. And what that is you say, well, what's the difference in velocities of the two objects after the collision compared to before the collision? Just take that ratio, okay? So the difference after compared to difference before. Okay, let's do a quick example. Suppose after the collision, you have 20 meters per second to the right and 10 meters per second to the left. Guys, what is the difference between 20 to the right and 10 to the left? And it's not 10, it's what? 30. Right. Now let's say before it was like maybe 25 to the right and maybe like 5 to the left. Right. Wait, what did I just do something? Hold on. Wait a second. Yeah, what's the difference between 25 to the right and 5 to the left? Would be 30 also, right? Okay. So you got a difference of 30 there, got a difference in 30 there. Okay, so 30 over 30, that would be like, that would give you coefficient of restitution of what? That'd be 1, right? Right. Actually, if you take directions into account, the fact that everything kind of reverses direction, it'll naturally come out to -1. So that's why I have absolute value bars here. Right. So it would take something that always would naturally be a negative number, it just makes it positive. Right. Alternatively, you could do the differences over the differences and slap on a negative sign. Or if you look really close, there's actually something funny about the way I wrote this fraction on the right side. Okay. Yeah, okay, final minus final, that makes sense, over initial minus initial. Oh, what's this? B minus A over A minus B? So I swap the objects, they're like backwards, right? Which looks out of place, it is, but intentionally so that overall this fraction is forced to come out positive rather than negative. Okay, okay, so that's the way you can quantify how bouncy is something. AP will never ask you a question, or I've never seen AP ask a question about this, so they won't, but always good to have a bigger picture of how you can solve things in this class, right? Bigger picture physics, right? If you do have a coefficient of restitution of 1, that is actually a special kind of collision. What kind of collision do you think that corresponds to? Perfectly elastic. Yeah, perfectly elastic. So I just gave you guys some numbers with velocities. If we also put in some mass values and calculated the kinetic energy, blah, 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 that would go along with that. Yeah, kinetic energy would be conserved with the numbers I gave you because the coefficient of restitution comes out to 1. Right? Hey, I wonder what is the other extreme coefficient of restitution you can have? What if two objects collide and stick? If they collide and stick, that means they have the same final velocity, right? Oh, which means that the difference in final velocities would always be what? 0, right? If they're moving together at like 3 meters per second. 3 minus 3, yes, that would be 0. Hey, what is 0 divided by anything every time? 0. So do you guys see your coefficient of restitution to quantify how bouncy is something is always between 0 and 1? So 0 is inelastic, 1 is elastic. And then if you have like 2 half-deflated tennis balls that, I don't know, maybe it's like 0.4 or something like that. Okay? Now, a special kind of setup you can do with this is, what if one of your objects is like a bouncy ball and the other object is like the entire Earth, right? So you have two things colliding and one of them is so massive it's basically not moving, right? Well, you could do a special setup where the difference in velocities post compared to pre, well, you could just focus on one object because the other object, the Earth, is basically not moving, right? So you could do rebound speed compared to crash speed, right? It reverses direction. That's why I got absolute value bars again, right? Rebound speed compared to crash speed. But maybe that's kind of hard to measure. But you know what's probably pretty easy to measure is to break out a meter stick and just measure what's my drop height, what's my rebound height, and then you can calculate those speeds, right? And you guys know how to do that. Last week you did conservation of energy, or even going back all the way to August with kinematic motion, you could have figured this out then too, right? it's always going to be square root 2gh for the speed, isn't it? Right? The rebound speed, square root 2gh playing off the rebound height, and the crash speed, square root 2gh playing off the drop height. So maybe you drop it from 100 centimeters and it boing rebounds up to like 70 centimeters, right? You could figure out the speeds, take the ratio of that would tell you coefficient of restitution. Now, big picture, it looks like the 2 and the g cancel. And so it just becomes square root of the ratio of the heights, right? That also represents coefficient of restitution. Okay, here's the lab table version of that. Probably have you guys do sometime in the next couple of weeks, right? Maybe give you guys different bouncy balls. You can quantify, ooh, how bouncy are these different bouncy balls off this tile floor? Ooh, got some kind of collision going on. All right, next big idea, impulse. All right, so impulse is just a fancy name for change in momentum. That's all it is. So, okay, delta P, change in momentum. Oh, change in momentum. All right, the physics word for that is impulse. Okay. Oh, this, okay, and then, now within a closed system, you can't have a change in momentum, right? But if you have like an external force on some object, you just focus on that object, right, then it could change its own momentum. So suppose there's like a ball thrown, right? And it's like thrown at its own velocity to the left, and this bat, bam, like hits it and like reverses direction off to the right. Right? If you're just focused on the ball, then there would be an external force on the ball, so it could change the momentum, right? Oh, I got a graph here. Force versus time. Hey, force versus time. You know what that almost reminds me of that you guys saw recently? Do you guys remember recently seeing a graph that was like force versus distance? You guys remember that? And okay, so my poster example here, I got a constant force, and the area under that curve, therefore, was a rectangle that represented an energy transfer, and I was calling that work, right? Now, this is a similar concept, but it's different units and it has a different application, right? Called impulse. So, okay, so work was a change in energy. Impulse is a change in momentum. It's the area under a force versus something graph, but this is force versus time, right? So last week was force versus distance. This week is force versus time. You are going to see both of these type graphs on the AP exam. You will, right? Maybe several times, right? You'll see several force versus distance. Whenever you see force versus, okay, think something to do with work and energy. When you see force versus time, think, okay, something to do with impulse and momentum. Okay. Now, oftentimes these graphs are like triangle shaped. Why would it be triangle shaped? Well, let's think through the mechanics of like a bat hitting the ball. Suppose you filmed that and you put it in slow motion, like 1,000 frames per second or something ridiculous. Right? Well, there's some point where the ball is going to start making contact with the bat, right? Maybe like opposite directions of traveling, right? And the bat pushes harder and harder and harder against the ball. And then at this point, this is like maximum force of the bat against the ball. And then the ball reverses direction, right? And then less and less push until finally at this point, the ball makes contact with the bat. And now it's like flying off the opposite direction, like that. Right? Okay, so that's why these graphs are usually triangle shaped. They don't have to be. It could be a rectangle shape too, but usually triangle shaped. Right? Right. And then if you take the area under that, that represents a change in momentum. Right? Like mass time change of velocity is usually how it's represented, right? Because usually you have a constant mass and you can be changing your velocity. Right? And what's going to get you there is like something to do with like force times time. And if it's a variable force, then again, just take the area under the force versus time curve. Right? Or you can think of it like an average force times time. And that's actually what this rectangle here is. Right? You guys see that this rectangle and this triangle have the same area? You see it? Because they represent the same impulse. Right? So have you guys in calculus done average value yet? Average value in calculus? Okay. So when you get around to that, here, I'll tell you exactly how you do it. Right? Isn't the area of a rectangle just base times height? So if you knew the area and you divided by the base, that would give you the height, wouldn't it? Area divided by base is the height, right? And how do you do that? Well, if these areas are supposed to be the same, like if this area of this triangle was, let's say it was like an iceberg, you know, let the ice melt, assuming the volume doesn't change, right? If the ice melts down, it's going to melt down to some level, right? Okay, so they'd have the same area. So if you get the area under that triangle and you divide by the base, which is the time interval, that's what delta t is, time interval, right? That'll tell you what the average force is. Okay, so you guys get average force times time be that rectangle, it's the same thing, right? Okay, all right. How about this? I'm showing mass times change of velocity to represent change in momentum. Doesn't necessarily have to be true. I'll give you guys a counterexample to what's on this poster, right? What if, and I've never seen AP ask a question like this, but what if maybe you're a systems engineer one day and you're designing some factory and maybe you have a conveyor belt, right? There's a conveyor belt moving along, and there's like masses being dropped, like blurp, 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 like some kind of changing mass. Ooh, could you have a changing mass? And you could have that conveyor belt moving at constant velocity. That would require some force to move it, wouldn't it? Ooh, okay, something like that. Right? So that's that's like a counterexample to what you usually see. You have a constant mass like a ball, and it changes its velocity, something like that. Okay. Oh, speaking of change of velocity, let's see if you guys remember vectors. Right? So when the ball gets thrown at 10 meters per second to the left, and the bat, bam, hits at 20 meters per second to the right. What is the difference between 10 to the left and 20 to the right? 30 meters per second. So that delta V would be 30 meters per second for that example. Because it reverses direction, right? Oh, closed systems and open systems. So you guys have got different perspectives on these. Last week, the definition of closed system was that there's no energy entering or leaving the system. And I said what goes hand in hand with that is that there's no external force on the system. And now you guys have a new perspective, which is that momentum is conserved also within that closed system. They all go hand in hand. If there's no external force and no energy entering and leaving, that also goes hand in hand with momentum is conserved. Okay? If there's an open system, let's see, energy could be entering or leaving. There could be an external force. And there could also therefore be a change in momentum because force times time interval. That's what that would represent, right? Do plus or minus because you've got vectors, okay? Something like that. Closed and open systems. All right. Next one. Ooh, ballistic pendulum. I do have an animation for this one too. So this is a really classic physics question. It's a little bit complex. It's like a 2 or 3 parts. Right? How you divvy this up. Right? So what have I got going on here? I got a bullet that's bam fired into a block. It's gonna swing up to some height. Right? That's like the entire mechanics of what goes on. Right? And what could this be useful for? The question that you usually get with a ballistic pendulum like this is, well, what was the firing speed of the bullet? What was the firing speed of the bullet? Okay. So in time order, what happens is that this bullet collides with the block, usually embeds itself in the block. You could call that a perfectly inelastic collision. Or you could also have a variation on that where that doesn't happen, but usually happens. Right? And then the bullet plus block together swings up. Oh, undergoes a height change. Hey, that sounds like conservation of energy. Hey, you guys remember last week? If you like start on a vine, you swing down, or figure out what's the maximum speed at the bottom. This looks a lot like that, just in reverse. Right? So it's setting up some height, right? And that height change is tied something to do with like the length of the pendulum times the angle it swings up to, right? You guys remember height change? What was it? I think it was L times 1 minus cosine theta, something like that, right? You guys remember from last couple weeks, right? So suppose it's like the year 1880. Right? We got the new revolver. I wonder how fast this thing can shoot, right? So how are we gonna figure out? It's 1880. We don't have a radar gun. Hey, let's just rig up a pendulum and let's fire the bullet, bam, into the block. See like how far it swings up, and then in principle, you have enough information you could solve this. So how do you use? You actually solve it backwards in time. So first thing you do is say, well, how high did it swing up to, right? And then use that to figure out how fast it got going post collision, right? And that's this right here. So how high it swung up to, it ends up with a bunch of potential energy that came from the kinetic energy that started swinging, right? Now it's both the bullet and the block, but even if you forget that, that's okay because the mass cancels out. And oh, look at that! The post-collision velocity is square root 2gh, which you guys have seen over and over and over again in this class, right? Speed is square root 2gh. Okay, so that's all fine, good. But and remember that h is really L times 1 minus cosine theta if you have to go that extra step deeper, right? Which I didn't quite cram onto this poster. Right? But where did that post-collision speed come from? Well, it came from this collision. So now we have to bring in collision physics. So that's why I've saved this poster for today, right? Momentum is conserved. All the momentum is supplied initially by the fired bullet. And here's our goal. We got to figure out what was the speed of the bullet. Right? Embeds in the block, perfectly inelastic. Collision makes one giant mass moving at some post-collision velocity. How fast? Oh, this fast right here, square root 2gh. Feeds them right there. Boom, you got your answer. Okay. Now you can figure out the firing speed of a bullet with a ballistic pendulum. Right. And last poster. Can you take this into 2 dimensions? Because if you paid real close attention so far, everything we've done is in just 1 dimension, like along the x-axis, which by the way is all AP will ever ask you. AP doesn't ask 2D collision questions, so this is a little bit beyond the scope of AP, but yeah, good to know this. Plus you may see this in college, right? Let's say you're playing billiards and you gotta strike the cue ball and bam, slam into the summon ball into the corner pocket or something, right? But like once you strike the cue ball, everything's set into motion. Everything that's about to happen in like the next 10 seconds is determinable, right? In principle. Right? So how does this work? collision physics. I bet these billiard balls are really elastic. I don't know what the coefficient of restitution is, but I'm gonna guess it's like 0.9 something, like really bouncy balls. Okay? And then what? Well, you could say momentum is conserved, and since it's a vector quantity, it's also conserved along each axis, x-axis, y-axis. So however hard you hit this ball, mass times velocity is gonna bam. At this point, you could do mv in the x direction for the red ball and mv in the x direction for the green ball, like component vectors, right? And it would have to equate, right? But what about the y direction? Well, if you hit this ball directly in the x direction, then in the y direction, there is zero momentum, which means that, bam, post-collision, this ball going upish and this ball going downish have to exactly cancel each other out, right? So that there's zero momentum ever. Yeah, you could have a positive and negative number that's zero out. You could do that, right? Everybody good so far? Right. Again, that's a little bit of, there's a textbook question. I didn't circle it like assign it, but I did print it. So if you want a good challenge question, or you know what else this could be? Could you do some reverse? What if there's two cars that collide and crash, like right to left? And then, yeah, like a crashing cars situation too. Yep. All right, let's switch over to video demos. Then we'll switch back for. Okay, go back forth here. All right, first, okay, we're gonna get up to that, but one thing at a time here. Let's look at. Rewind. Okay. All right, so what you got here? It's got a basketball, a tennis ball, and I'll call it a golf ball. I think it might something like that. All right. So what if you just had one of those balls in isolation? Like, what if you just had the golf ball, like just the golf ball, and drops it? Like in principle, how high could it at a maximum rebound to? Like, its original height, right? And realistically, it'll never quite reach that place, but it could definitely never go above that, right? But what if you throw in the tennis ball and the basketball? How's this gonna play out now? Bam! Whoa! You see it like shoot like way to the top of the camera? Bam! Right. Okay. And the explanation for that is that those top balls, like the tennis ball and the golf ball, were taking momentum from the basketball, right? Or what if you just focus on the basketball? Like if you in isolation just drop the basketball, it would rebound to some height, right? But if now it's sharing its momentum with the two balls above it, do you think it's gonna probably not rebound as high? Ooh, because it's giving some momentum away, right? Okay, so that's a fun one there. I got a ballistic pendulum. Okay, so hopefully when I was going over the poster version of this is what you had in your mind, right? Okay, so that bullet fired, bam, sends this pendulum up to some height, right? Or actually some angle, right? I guess we got was that about like 23 degrees or something right there, right? Okay, so if you know that angle, the length of the pendulum, you can calculate the height change. Where did that height change come from? Well, it came from, let's see, it had some kinetic energy there. Where did that kinetic energy come from? Well, it came from, there was this inelastic collision. Therefore, you can back calculate what was the original firing speed of the bullet. Okay, so you solve this whole thing backward in time, conservation of energy to conservation of momentum. Okay, and last demo I got for you guys. Let's check out this magic school bus. So these kids go inside this textbook that has zero friction. Got a zero friction field. Right, they're gonna play a game of baseball on zero friction field. There's an hell over here. Oh, look, everybody's having trouble maintaining balance. You guys see that? Right. You guys ever gone ice skating? The first couple of times you go, really hard to maintain your balance, right? Because there's hardly any friction. So the ground is really unforgiving, right? You have to maintain your center mass like right above your feet, right? Okay, so hard to maintain balance. All right, and if I zoom ahead, I'm gonna skip past her throwing this ball. So, okay, yeah, got a scuffer. All right. Throw it. Whoa. Oh, and she gets kicked back the opposite way, which may be not super surprising because that's like Newton's third law of motion, right? She throws the ball forward, she gets kicked back the other way, right? Hey, if I told you how fast she threw the ball and what was the mass of the ball and what's her mass, do you think there's enough information there that you could calculate how fast she's headed back towards second base, right? Okay, you actually could have done that before today, but I'll tell you how you would have done it before today. It would have been a long, complicated process. Here's what we've done. Say, well, see if I know the speed of the baseball head towards home plate I can say, well, it had to have gotten up to that speed starting from rest. So it had to have undergone an acceleration over some small time interval of her throwing it, maybe a tiny fraction of a second that she threw it. Okay. Therefore, multiplied by the mass of the baseball, you can figure out what force was thrown on the baseball to give it that acceleration, to give it that final speed. It's the same force acting on her in the opposite direction because of Newton's third law of motion. Bring in Newton's third law. Right? Then divide by her mass, you can get her acceleration over the same time interval, go back to kinematic motion, and then you can figure out how fast you go. Okay, that's a long like process, right? Oh, they could, but there's a much faster way to also answer that same question, and that's conservation of momentum. You say, well, very simply, she and the ball had 0 momentum to start with, just on the mound. So mass times velocity of the ball towards the plate equals mass times velocity of her headed back towards second base. Boom. You know the 3 variables, solve for the 4th, done deal. Okay, how do you say? Right, let's roll this forward a little bit. Let's see how it's going to play out. All right. What happens when he hits this ball? Oh, it goes into a spin, right? Okay, now that might involve maybe something called a torque we haven't quite gone to yet, but if he hits the ball, see there's some like radial distance that he hits it, it's gonna like give him like a turning type motion, right? Every time you open a door, right? Same thing, or use a wrench, it's like a torque. Talk about that in December. So he's spinning. Oh, yeah, everybody on the field is kind of stuck in place, right? I mean, if there's no friction to push against, you're just kind of stuck where you are, right? Right? Maybe unless you like take your hat off and throw it really hard one direction. Otherwise, you're just stuck. Right? This is pretty similar to space physics, right? Like you're in space and you started spinning, something hits you to make you start spinning. That's it. You can't stop spinning, right? Once you're in motion, drifting some way, you can't like stop drifting that way, right? Right? Just take gravity out of this. Now you got space. Right? Ooh, it's like a really bouncy ball. No friction to slow it down. I'll get going. Crazy time. Boing. All right, let's do some puzzles off this half page here. Half page. All right, so this half page I'll eventually pick up from you guys. So as long as you're following along, then you'll be all right here. I've got lots of different versions of this. So my numbers may or may not match your numbers, but we all have the same questions otherwise. Right? Ooh, equation bank. Here's general conservation of momentum. Right beneath that, perfectly inelastic. It's pretty similar. It starts out the same, but just they stick together. Common final velocity. The one to the right of that, perfectly elastic. Now that's that solution system of equations. One above that is impulse, change of momentum, mass times change of velocity, force times time interval. Right? And then off at the top right, coefficient of restitution. That's the way you can quantify how bouncy something. There's actually 2 equations all shoved in one line there. Okay, here. All right. Question number 1. 2 objects collide and boing, bounce off each other so that the kinetic energy of the system is conserved after the collision. For example, Newton's cradle. That collision is called elastic. Question 2. 2 objects collide and stick together so that some of the kinetic energy is converted to other type of energy. For example, like permanent deformation. Hey, one football player tackles another football player. That's a what kind of collision? Inelastic. Boom, boom. There you go. Okay. Like perfectly for each one of those, right? So kind of extreme condition. All right, question 3. 2 objects collide and stick together, resulting in these given measurements. What's the final velocity of object B? Okay, so I gave you the mass of each object, each pre-collision velocity, and one of the post-collision velocities. That's for the other. So I'm gonna get a picture going and then start plugging in numbers here. This is number 3. So I got like some mass A, some velocity A initial, and then some different mass B. Maybe I don't know. These are like 2 asteroids or something out in deep space. Move it at some velocity B initial. Right? And if it's a head-on collision, like opposite direction, then I hope those 2 velocities, well, one's positive and one's negative. They should have opposite signs, right? Let's see if that's the case. I got a positive versus a negative velocity. Right? You could have a collision where they have the same sign velocity. That would just mean here, if they're both positive, that could be like a fast car runs into a slow car. Bam. Like you guys remember Speedy Sue in the van in the tunnel? Right? That could be like the same direction. They could have both positive. All right, let's do. I see there's going to be bam. There's going to be some kind of collision. So once I see that there's a collision, the first thing I think is conservation of momentum. Sum of momentum initial equals sum of momentum final. initial is before collision, final is after collision. Right. Then, okay, we got two individual objects. Keep track of their momentum. They're all along the x-axis, so that's all good. Mass A, velocity A initial, plus mass B, velocity B initial, equals mass A, velocity A final, plus mass B, velocity B final. There you go. Here's conservation of momentum. Right? Oh, I bet I could just do some plugging and chugging right here. Okay. I've seen AP ask some basic questions about, basically this you could use. Right? So, gonna grab the numbers off my paper, which are probably different than your paper. I've got 4 kilograms there and there versus 3 kilograms there and there. Got 7 versus -9 meters per second. So there's 7 meters per second to the right. Got -9 meters per second, so it's come back the other way. Pack those together equals, and then let me do a pause right here. Suppose that's all I gave you. Suppose I gave you nothing else. Right? Would this be solvable? No, because there would be 2 unknowns in one equation, right? You know what else you wouldn't know? You wouldn't know what kind of collision it was. Is it 2 balls of clay? Is it 2 boing, really bouncy balls? Is it 2 half-deflated tennis balls? It could be one of a billion different types of setups, right? We don't know. Right? So I have to tell you something else. In this case, I did, of course. I told you velocity A final. So let's plug in that number. And on my page, it looks like this. Okay. So now, once I tell you that number, okay, at this point, it becomes exactly determinable what velocity B final F is. So we'll call it BBF. Vector, solve for that. Okay. All right. And you guys could navigate this algebra, right? So put all this together. That times that, minus that times that. Okay. Oh, okay. It looks like I have this many kilogram meter per second. Is that right? Yeah, 28 minus 27. Okay. The momentum got this many kilogram meter per second here. Plus 3 kilogram BBF right there. Okay. Add this over, divide by that. Okay, what? That. Okay. I'm getting BB final is, and I got a number, and that's meters per second because it's a velocity, right? Meters per second. Right. Make sure it's an answer choice. Yeah, that's an answer choice. Bam, right there. So I think we're in good shape so far. Okay. Ooh, yeah, these things are like rebounding off each other pretty good, right? Okay. Oh, one more thing I want to fit in before the bell here. Let me do a kinetic energy check. Let's do a kinetic energy check. Because supposedly the kinetic energy either stays the same or it decreases, but it can't do anything else. So kinetic energy initial is 1/2 mv squared for object A plus 1/2 mv squared for object B. And then I'll do kinetic energy final, and same thing, 1/2 mv squared final plus 1/2 mv squared. Okay, right. Let me just beat the clock here. I'm going to just plug the numbers here. So 1/2 times that mass times that speed squared plus 1/2 times the other mass times the other speed squared. Looking at, I got 219.5 joules to start with. Okay. What about after the collision? After the collision. So 1/2 times m times v squared plus 1/2 times m times this v squared. All right, I'm getting, like 80.2 joule. Okay, yeah, the kinetic energy definitely went down. Kinetic energy post-collision is smaller than kinetic energy pre-collision. Okay, so we're good. Okay, I mean, this is one of these things like conservation of momentum. Say you guys are a physics teacher someday, and you're just setting up your own equations. If you don't keep track of kinetic energy, it's easy to like reverse the direction, like have it in time reverse, right? And you wouldn't know just from conservation of momentum, like what happened before and what happened after. But if you keep an eye on kinetic energy, then you can tell. It has to happen from here to here. It can't go from here to here, right? Because that would be, unless it was like an explosion, Right? So there's like a grenade situation. All right, so that's a good pause point. You guys have a great rest of your day. More adventuring tomorrow.